So I'm going to do a series of integrations of increasing powers of trig functions. So I'm going to start off with sine squared x, which we cannot integrate directly. But what I can do is I can use one of the trig identities from the double angle formulae, which I'm going to put over here. Cos 2x is equivalent to 1 minus 2 sine squared x. Now obviously I've chosen this one because it has the similarity of the sine squareds that we're after. So if we rearrange the identity, I'm going to subtract cos 2x from both sides and add 2 sine squared x. So I get 2 sine squared x is equivalent to 1 minus cos 2x. And just multiply through by a half and I get what I want on the left hand side. Sine squared x is a half brackets 1 minus cos 2x. So I can now substitute my identity into my integral. So my integral now becomes the integral of, I'm going to take the half outside because it's a constant, and I'm going to have 1 minus cos 2x dx inside my integral. Now I can integrate that directly because it's a fairly straightforward process now. So I have a half, and inside I have integral of 1 is x, and I know that sine differentiates to cos, so cos integrates back to sine with no change of sign. So I'll go subtract, and because of our 2 in front of the x inside the cos function, I'm going to take that into a half sine 2x plus c. Multiply through, end up with a half x minus a quarter sine 2x plus c, and we're done. So we've now gone up to a cubed power. Now the technique I'm going to show you now is actually useful for any odd power of x or odd power of sine x. So in this case we've got an odd power sine cubed. I can use a substitution method. Now that does not necessarily seem intuitive, but I'm going to change my integral so that it becomes sine x multiplied by sine squared x dx. And I'm going to use a substitution u. Now you might want to throw in sine x. It seems logical, but actually if we put our substitution as the derivative of sine x, something nice happens. Because we want to replace dx with du, as with any substitution. So du by dx, cos goes to negative sine. Get dx by himself, so we get negative du upon sine x. I rearrange it. And if I substitute that in place of dx on my right hand side in my integral, I get sine x. I'm going to take my negative sign outside, times sine squared x du all over sine x. Now conveniently, because of the substitution I chose, my sine x now cancel. My integral becomes that little bit easier. So we've now got sine squared x du. Of course, I can't integrate that yet because I have the function in terms of x, and I'm integrating at the moment with respect to u. However, what I do know is sine squared x is the same as 1 minus cos squared x. And I also know that cos squared x from my substitution is the same as u squared. So I can replace my sine squared x with 1 minus u squared. And now I can place that into my integral, and I end up with 1 minus u squared in brackets du. So I now actually have my integral in terms of u, so I can go ahead and process it into that integral. I'm going to move over here. So my integral becomes negative, integrate 1, I get u, integrate u squared, I get a third u cubed, and of course plus c. So that becomes negative u, which is negative cos x minus, multiplied by minus is plus, a third u cubed. From our substitution, I know that's cos cubed x plus c. Let's tidy it up a little bit. I'm going to put my third cos cubed x because it's positive there and it's a higher power, minus cos x plus c. And there we have it, we're done. So things are getting a bit tastier now. We've increased the power once again to sine to the 4x. Being an even power, we can't use our substitution method. Now, whether or not you're doing A-level maths or further maths will depend upon which avenue of attack that's open to you. So I'm going to go ahead and use a method that's actually accessible to both A-level and maths and A-level further maths. So I'm going to rewrite my integral, sine squared x multiplied by sine squared x dx. So that allows us to use a substitution which we're familiar with. I know that sine squared x from earlier on in the video is equivalent to a half brackets 1 minus cos 2x. Okay, so if we plug that in place of sine squared x and multiply them out, I end up with a quarter at the front from my half times a half, and then I end up with 1 minus cos 2x all squared dx. So if I multiply 1 minus cos 2x out, I end up with another integral. So expanding that, I end up with 1 times 1 minus 1 times cos 2x twice. So it's 2 cos 2x, and then negative cos 2x multiplied by itself plus cos squared 2x dx. So what I've now achieved is I've got two terms which are now, if the word integratable exists, they can be integrated, and I've also got another term which is a little bit more problematic, but we can once again use another one of the double angle identities, and I can basically say that cos squared 2x is equivalent to half brackets cos 4x plus 1. Okay, that comes from the double angle identity for cos x, or cos 2x in this case. So we're going to replace that. I'm going to move my integral over here because it's getting quite long to deal with. So I've got a quarter, 1 minus 2 cos, let's put a c in cos, shall we? That's probably a good idea. 2 cos 2x. Now I'm going to replace cos squared 2x to plus, I'm going to expand this out, a half cos 4x plus a half dx. I can collect my two numerical terms together, 1 and a half, to get 3 over 2. So my integral becomes a quarter integral of 3 over 2 minus 2 cos 2x plus a half cos 4x dx. I'm now going to move on to another board because that's gotten a little bit big for its boots now. Okay, so if I place that there, I'm going to copy my integral up to here, and we're going to get 3 over 2 minus 2 cos 2x plus a half cos 4x dx. Okay, so we can now integrate that term by term. You can see above that the identities that I've used. To simplify, I say simplify and make this integral look worse than it started, but actually it's much easier to integrate now. So we're going to get a quarter on the outside, 3 over 2x integrated from 3 over 2, and sine differentiates to cos, so I know I end up with the same sign on the outside of the trig function. Divide 3 by 2, so I end up with sine 2x, and once again my sign doesn't change because sine differentiates to cos, so cos integrates back to itself, so that becomes a half divided by our 4 on the outside from this 4 here, so it's 1 over 8 sine 4x plus our c. I'm going to multiply through by my quarter, so I end up with 3 8x minus a quarter sine 2x plus 1 over 32 sine 4x plus c. So that integral becomes a bit of a beast, but we've managed to slay it. So we're done.